In this video, we'll continue with nuclear chemistry, talking about decay series and the kinetics of nuclear reactions. Okay, so first let's do a practice question with the decay modes we talked about last time. What decay mode do we think would be the most likely to stabilize the nucleus of 24 neon? Okay, so the right answer for this one is a beta emission. How would we go about solving this problem? Well, first we want to look at the ratio of neutrons to protons in this species. So if it's neon, we know that this is going to be 10 protons, so we'd find this from the periodic table. Remember, A is equal to n plus z, so to find the number of neutrons would take 24 minus 10, and that would be 14 neutrons. So in this case, we can see that we have more neutrons than protons, and for relatively light nuclei, this is unstable. We want about a 1-to-1 ratio for neutrons to protons. So this is telling us that we have too many neutrons, or not enough protons. So we want to find a type of decay mode that is going to correct this problem from the options that are in the list. So if we look at beta emission, we can see that in order to balance this, because the beta has this -1 in the z range, this is going to give us an extra z in the product without changing the A, and so it'll make this ratio of neutrons to protons closer, giving us a more stable nucleus. Sometimes when a nucleus undergoes a reaction, the product is still not stable, so it might make something that's more stable but still not completely stable enough. If this is the case, the nucleus will undergo several reactions until it reaches the band of stability, or one of those points where the ratio between neutrons and protons gives us a stable nucleus. This is very common with extremely heavy isotopes, so things like uranium. If it decays just by one step, we will lower the number of neutrons and protons, but we'd see that we'd still end up with a species that isn't still completely stable. In the case of uranium, this will undergo 14 steps to get us to a stable lead nucleus. And really anything that's heavier than lead isn't going to be completely stable. It might have a long lifetime, but it'll go some kind of spontaneous decay until we get down to this lead nucleus. So one of the things we might want to try and do in this case is find out how many decay steps, if we're given that these are alpha and beta decays, how many of each are there to get to this point. We can do this again looking at the equations for the reactions. So remember, an alpha decay is going to release an alpha particle, and a beta decay is going to release this beta particle. This alpha decay is going to be our only way to change A. So we can find out how many of these that we need in order to get to this lead 206 nucleus. So if we do 238 minus 206, we get that we have to change A by 32. Every alpha decay is going to change this by 4. So if we do 32 divided by 4, we get that we need 8 of these alpha decays to get down to the A that we need. So after 8 alpha decays, where would that leave us from this uranium? So we'd have 238, 92, and if we had 8 alpha particles, in order for this to balance, we would also have to change the Z by 8 times 2, so that would be 16. And so that would give us the right number for the mass number, but it would give us 92 minus 16, or 76 for the Z. In order to make this 82, we can do the beta decay. That'll only change the Z. And we see that we need to increase it by 6. And we can see each one of these betas is going to be for 1. So this gives us 8 alpha decays and 6 beta steps to get to this product. So most of these nuclear reactions are going to undergo first order kinetics. If we look at the decay of uranium, so one of these many steps, the first step, uranium to thorium, We can think about this if this was an elementary step. There is only one reactant, so this would give us a first order step for this process. Remember, the first ordered integrated rate law has this form where our concentration at a given amount of time is going to equal our initial concentration times e to the negative kt. You'll often hear half-lives associated with these nuclear reactions, and as a reminder, this is the time it takes half of the original amount to react. And for these first order reactions, T1 half is going to be equal to the natural log of 2 divided by whatever the rate constant is for the reaction. Remember that for first order reactions, the half-life is going to be independent of the initial concentration. Here's an example of a decay of several half-lives from a molybdenum-99 isotope. Remember also that with the half-life, it's going to split in half for every one of those intervals. So in this case, the half-life of the molybdenum-99 is 67 hours. So if we start with 1 milligram, after the first 67 hours, we'll cut that by half. After the second 67 hours, we'll cut the half in half again, or we'll end up with a quarter. By the third half-life, we'll have cut this into an eighth, and so on and so forth. And each of those is going to take 67 hours. The main thing that we're thinking about when we're talking about these decay reactions, especially of harmful nuclei and their number of half-lives, is how many of these half-lives it would take to split it in half far enough so that it's under a safe threshold. So let's look at using one of these rate laws for a calculation. We have this polonium-208, and we're going to say this undergoes alpha decay with a half-life of 2.90 years. If a sample of polonium-208 initially weighed 20 grams was decaying for 4.5 years, what mass of the polonium would be remaining? So let's set this up. We have our half-life is equal to 2.90 years. And remember, we can find k because the half-life is equal to the natural log of 2 divided by k. So solving for k, we get k is equal to 0.239. And in this case, since the T1 half was in years, our rate constant will be in years to the minus 1. And so the amount of polonium that we have is going to be equal to the initial amount times e to the negative k, 0.239, times the time, and it gives us is 4.5 years. And so if we plug all of that in, we get 6.82 grams.